Hello everyone, my name is Emmanuel. I'm a student at the Federal University of Catalan, currently pursuing a master's degree in modeling and optimization under the guidance of Professor Holmes. In this presentation, we'll have a brief discussion of the paper named A Stochastic Surrogate Modeling of a Nonlinear Time-Delay Mechanical System. In the introduction section, I'll talk about nonlinear time-delay systems and the uncertainties that these systems may present. Then, I'll show the two types of surrogate models used in the paper to solve our problem, which you can see in the third bullet, the nonlinear time-delay mechanical system. In the next item, I'll discuss the numerical results and, at last, I will provide some conclusions. Nonlinear time delay is a phenomenon that can be seen in a variety of physical, chemical, and engineering problems. Take for instance the clap sound made by hands. The listener doesn't hear it instantly due to the sound wave speed, so we can infer a delay between the clap action and the listener. Another example is the field of control engineering, where you have a controller monitoring the state of a variable to make adjustments. Since these adjustments are never instantaneously, there is a delay between the variable observation and the control action. All these systems are subject to uncertainties, such as noise in a sensor monitoring the variable of control system, or the temperature in the room where the clap sound was made. Hence, it is important to propagate the uncertainties in these systems to capture the real dynamics of them. However, propagating uncertainties in these systems may increase the computational costs due to the complexity of the models and the number of simulations that we must run to retrieve the statistics. To circumvent this problem, we can build surrogate models, that is, a model that still captures the dynamics of the system but drastically reduces the computation cost. One of the surrogate models used in this paper is the polynomial chaos expansion. Here, the model is approximated by a set of orthogonal polynomials related to its variable joint probability distribution. So, we can express our model f of x and t by a summation of polynomials multiplied by their coefficients. We have two types of approaches: the intrusive, where it requires to rewrite an existing code to target the PCE. The second approach is the non-intrusive method, where we run the deterministic model several times and we use a collocation method to fit the polynomial expansion. Since the non-intrusive method doesn't require changing the existing code, we chose this method. In our case, we have used the least square approximation to calculate the coefficients of the expansion. The other surrogate model approach is the Karhunen-Loève decomposition radial-based function method. Since it's a big name, I'll just call it KLD from now on. The idea of this method is to first reduce the dimensionality of the model by decomposing it into a set of orthogonal proper functions by using the key KLD. The reduced model is obtained after picking the largest eigenvalues of the decomposition, which I'll demonstrate in the next slide. The next step is to approximate the reduced model by using a set of radial basis functions. Here we call it just RBF, which you can think of as a simple kind of neural network. First, we sample our random variables and create a snapshot matrix S. This matrix will contain the response of our deterministic model. Then, we multiply the matrix S by its transpose to obtain the matrix C. From matrix C, we calculate its eigenvalues and eigenvectors. The next step is to calculate the amplitude matrix A. We obtain this matrix by multiplying the transpose of the eigenvectors matrix phi with the snapshot matrix S. The reduced model is obtained by selecting only the largest eigenvalues associated with the corresponding eigenvectors. In this case, we have the S approx. All these steps conclude the KLD. To interpolate the reduced model, we do the following. First, we select a type of basis functions. In this case, we picked a linear spline function. You can see here as G. Then, we compute matrix G, here called big G. After computing big G, we obtain the interpolation matrix B by multiplying the inverse of big G matrix with the reduced amplitude matrix, which is our reduced model. This step completes the interpolation process. So, in order to run a simulation with the surrogate model, we take a sample of our vector of random variables x and compute the matrix small g. After that, the response of our model, in this case u of x, is obtained by multiplying the reduced eigenvector matrix with the interpolation matrix B and the computed matrix small g. In this section, we consider the 2-degree of freedom model shown in the figure. This model consists of a primary system attached to the ground by a suspension that includes a nonlinear damping and a nonlinear spring, and a dampened secondary mass coupled to the primary system by a spring with nonlinear characteristics. The secondary system is submitted to a time delay, which is known a priori. The purpose of the observer M2 is to suppress the amplitude of oscillation of the main system. However, as the systems are coupled, it is necessary to take into account the contact force, which explains the presence of the parametric force given by the term x1 times f2, cosine of sigma 2 times t. Here, we can see the set of nonlinear ordinary differential equations that we must solve to get the displacement of the primary structure. As we can see, the velocity terms x.1 and x.2 are functions of the time delay, thus resulting in a complex dynamic behavior. In the set of equations, we will consider the time delay tau, the damping eta2, and the stiffness ratio kappa as our random variables to build the surrogate models. Now we are entering the numerical results and discussion. We'll briefly discuss about the order of the PCE that best fit the system displacement response. Then I'll show the results of both surrogate models and their computation times. For the PCE, 500 samples were taken from the uniform distribution to build the surrogate model. We can see the lower and upper limits for each variable in the table below. In this plot, we can see the PCE order approximation. Starting from order 1, we don't see a good fit with the deterministic model. As we increase the order, the mean square error decreases and we finally obtain a good curve fit. For the KLD method, we first create a design space. For our problem, we select 10 equally spaced points between the lower and upper limits of each variable. Compared to PCE, we didn't have to pick too many samples to build this surrogate model based on KLD. These two plots show the displacement of the primary structure. On top, we can see the overlay of the PCE surrogate model and the deterministic model. We can notice that the surrogate is able to reproduce the displacement as if it were the deterministic model. The same idea applies to the KLD model. In both cases, we only use the time delay as the random variable. Here, we are using the 3 parameters as random variables. Again, we notice good agreement between the deterministic and the surrogate model. Having said that, as the name implies, we can use our surrogate model rather than the original to emulate the displacement of the primary structure without losing the time delay characteristic of the system. The other advantage of the surrogate model is the computation time. Notice that the PCE with random tau takes only 9.5% of the time compared to the original model. So, we can conclude that both stochastic modeling approaches, the PCE and the KL-DRBF, are able to build a surrogate model of a nonlinear time delay problem. Moreover, the models presented a lower computation time cost compared to the deterministic model, and that the PCE had a lower computation cost compared to KLD. Thanks for your attention, and feel free to comment the results of this paper.